Good. So welcome to our speaker and Dr. Hu. So Dr. Hu is from the Department of Physics at McGill University. He was having his PhD study with Professor Hong Guo and just received his PhD degree like in this April. Dr. Hu is a very brilliant young scholar in the field of computational condensed matter physics and topological physics, with first author publications on physical review letters, nanoletters, natural communications, matter, and extra. In today's talk, Dr. Hu will talk about his work on using topological nanotubes to achieve low dissipation electron transports. His findings are very useful in applications of electronic devices and quantum computing. Now I will give the time back to Dr. Hu. Yeah, please.
Okay, thank you. Thanks to Dr. Ying for the invitation, and it's my honor to come here and give this talk. And my talk, the title is Topological Nanotubes, Driving Electrons on the Highway. The topological physics is one of the hottest topics in nowadays condensed matter physics and material science. And also this nanotubes is a very famous 1D materials which has been used in a lot of technologies, nanoscience or nano devices. So in this talk, I will combine these two fields together, and we can realize this topological physics in the nanotubes. Okay, so in this talk, I will give some basic background about this topological physics and this nanotubes, carbon nanotubes, and a nanotube device, and then I will say how I can achieve this topological physics in the nanotubes. Okay. So my first page is about this heterostructures, which is now is very popular in nanoscience. This 2D materials has attracted a lot of attentions nowadays. So the most famous 2D materials is graphene, as we know. This graphene is a hexagonal lattice which is made by these carbon atoms. And also we can replace these carbon atoms with this boron or nitrogen or other atoms. We can get this boron-nitride, this 2D lattice. And also we can replace with another elements, and we can get a lot of different these 2D materials. And after we have studied all these kind of 2D materials, another thinking is that we can combine this together. We call this heterostructures. We just stack different layers together, and we can get these hetero layers. So by using these heterostructures, we can always get some new properties which didn't show up in the individual layers. So this is a new way, and it opens a new possibility for this material explorations. We can just mimic this way in the 1D materials. We know that in the 1D materials, the most famous one is the carbon nanotubes, and also we can replace these carbon atoms with boron or nitrogen. We get this boron-nitride nanotubes. We can just combine these different nanotubes together. We just put one into another one, and we can get these hetero nanotubes. So we can also think that if we use these heterostructures, we can expect new properties or new phenomenon which didn't show up in the individual nanotubes. So this is a basic frame of my work, is that I want to combine different nanotubes together, and I want to get some new properties. Okay, firstly, let's see some pure nanotubes. The first one is this carbon nanotubes. This is the most famous one, and it has been discovered for, I think it's over 13 years. And this carbon nanotubes is a 1D material. We can just say it is rolled up by this graphene, this lattice. This rolled up direction we call this chiral vector. It's a very important index of the carbon nanotubes, which is a pair of the integers. By using different chiral vector, we can get different nanotubes. So this nanotubes can be classified to different types. The first one is zigzag, which you can see this edge is like a zigzag type, and also this armchair, and also this chiral. So this this chiral vector we can use it to classify different these carbon nanotubes. In this study, I will focus on this arm shell, this one, which has a carrier vector NN, this M equals N. So for this, all this arm shell, this carbon nanotubes. Previous studies has told us that this arm shell carbon nanotubes are the metallic. So we can see these band structures. So the band structure, we can see this zero here is a Fermi level. We can see there are a lot of states. There are 2 states around this Fermi level. So it is a metallic structure. So it's conductive. We can see that all these arm shell are metallic. So here we just put one example here, 1906 and 1906. Another one is another famous one is this boron-nitride nanotubes. We just replace this carbon with boron and nitrogen atoms, and we just roll it up. We get this boron-nitride nanotubes. We can also have different boron-nitride nanotubes, liquid arm shell or carrier. And the most difference between this boron-nitride nanotubes BNNT and the carbon nanotubes CNT is that we can see that from this band structure we can see that all the boron-nitride nanotubes are insulating. You can see just around this Fermi level there are no states. There are a big band gap here. So we can see these boron-nitride nanotubes are a very good insulator. So let's think of just this pure carbon nanotubes or the pure boron-nitride nanotubes are very simple. Their properties are very simple. One is metallic and another one is insulator. So let's think about a very interesting question is that if we combine these 2 together, what will happen? So now we have a conductor, we have an insulator, and we just put it together. And because this carbon nanotube is the radius is smaller than the boron-nitride nanotubes, so it's inside this boron-nitride nanotubes. So if we just combine these 2 together, what will happen? So we can think of this. Firstly, we can just guess. It is still a conductor, or it's an insulator, or we can get something. It's neither a conductor nor an insulator. So this is the main purpose of our work, is that we build a heterostructures, and we want to see if we can get something new, different from these 2. Okay, firstly, let's see a very simple case, is that the inner carbon nanotube and the outer boron-nitride nanotube have the same carrier vector, N equals 19.6. And we can see this number is just an example. In fact, all our studies are very general to adding this number. So we can just see that we just take this N equals 19.6 as an example here. So firstly, we just study M equals 0. So the inner one, outer one have the same carrier vector 19.6, 19.6, and this also 19.6, 19.6. So this is so can you see my mouse here or this? Or Dr. Ying? I'm not sure if my mouse has showed up in the screen.
Yes, we can see the CCL mouse there.
Okay. So because this is I have this laser here, so I just use this as an indicator. Okay. So for here, we can see that this is a cross section view of this nanotubes. We just cut it and see this cross section, the circumference here. So we can see that for this one, the stacking. All the stacking around this circumference are the same. All is we call the commercial rate stacking. So all these are the same. It's like this stacking. So this stacking, we can see that if we calculate this band structure of this structure, so we can see this is the band structure. So we can see that now there's a band gap opening here. So now it's not conducting, or it's not a metallic. Now it's an insulator. So all these states are from this carbon nanotubes. The boron-nitride nanotubes, the states are very far away from the Fermi level. So we just study these states from this carbon nanotubes. And we can see that we just compare this one with the individual carbon nanotubes 19.6 without this boron-nitride nanotubes. We can see that for this one, it's a metallic, it's a metal. There are some states around the Fermi level. But after we add more nitride nanotubes here, this gap is opening, and now it's changed from a metal to an insulator. So this is the first conclusion we get, is that when we have boron-nitride nanotubes around this carbon nanotubes, we can change from a metal to an insulator. This is because this space symmetry has been broken. The space symmetry of this lattice has been broken by the boron-nitride nanotubes. I will not say a lot of this mathematical thing. I will just focus on the physical picture here. So is that after we add the boron-nitride nanotubes, changes from a metal to an insulator here. So this is a very simple phenomenon. It's just a metal insulator transition here. So of course this is not all of my what I will say in my talk. This is just a very simple part. So we can just think about this. Is there any other story in these systems, such as we just change its M here? So next page is that I just change its M from 0 to 1 to here. So in this case, let's calculate this band structure. Let's first guess. Shall we still get an insulator or metal or something different? So we just calculate it, and we find that we get a very strange band structures here. So firstly, let's see this green lines here. The green lines are the states which is from this carbon nanotubes. So you can see that it still has a band gap here, just like here. So we can see there's a band gap here. We just see the green lines here. There's also a band gap here. But we can see inside this band gap, there are two states crossing the Fermi level. So it's a conducting states. So the interesting thing is that why these states happen here. So why we can get this conducting state here? I will say in the following that in fact these states are topological states. It's not a trivial conducting states. Firstly, let's just analyze some properties of these states. So let's firstly analyze the wave functions of these states. For some audience who are not so familiar with the quantum mechanics or this solid state physics, they will say some background about this wave functions here. So we can see there are some states here. We just analyze the states. Where is their states from? So which atoms contribute to these states? So this is this plot. So this is also a cross section view. We just cut this one. These tubes. So this is a cross section view, and this is circumference. We just see the circumference here. We can see that this red one and this blue one, the two states come from different atoms of this carbon nanotubes. So now we can use academic word here. So this is we call the localization. So we can see the different states are localized at different spaces of this carbon nanotubes. So we can see that in these systems there are two types of electrons. We call the K and the K prime here. So this is just like a spin up and spin down. We know that electrons have some intrinsic properties such as charge or the spin. We know the charge have the positive or negative, and spin up and spin down. And also this K and K prime is another type of property. So we have K and K prime here. So we can just think it as a different degree of freedom. So we know that so for here, let's see what's happening here. So in the solid state physics, the band structure, this slope here, denotes different velocity. So this positive slope means that there are positive velocity of these electrons, and this negative slope means that we have a negative slope. We have a negative velocity here. So we just use this one. Then let's see that for this K electron of K here. So first, let's see the red one. The red one will have a positive slope, so it is transport is to the positive direction. And with the K prime here is a negative one, so it's a negative here. So it is located at this red this places. And also we can see there's a green one. The green one, this is another transport pathways. And for this one, we can see that this K prime is a positive one, and this K is a negative one. So we can get all the picture about this transport details in these structures. Okay, let's see what will happen if we add electric field. So if we just connect it into a circuit, we give an electric field, and now the electron will transport from left to right. So we have two kinds of electrons, just as I said before. The first one is the electrons of K. Another one is the electron with K prime. Okay, it's just like spin up and spin down. So we can see that this K electrons goes from left to right. As we know, in in the transport, sometimes we have some scattering. So this is why we have resistance. We know that in a device or in a circuit, if this in a structure there are some impurities or some disorders, when electron goes from in a direction, it will meet this disorder or the vacancies or this kind of impurities. It will be scattered from to another way. So then this resistance happens. So this is why we have resistance in our circuit. Is that there are some disorders or some impurities. So we have the scattering. So let's see that if we have electrons of K transport from left to right, if it meets some impurities, they will be scattered backwards. So this we call the back scattering. It's that we scatter to a positive way. But for here, we can see that if K is here, they cannot scatter to the K prime because there are different types of electrons. So it can only be scattered to this one. To this one. This is the K with opposite direction. But these two, in the real space, in the space, they are very largely separated. So they are very far away. So it's very hard. It's very hard for the electrons scatter from this pathway to this pathway because they are very far away in the space. So from this we know that in fact these electrons goes in this nanotubes. It can very difficult to be back scattered. So in other words, in this transport, it is a very no dissipation because there is no back scattering happens. So the same one. So the same philosophy can be applied to the K prime here. So the K prime goes in the green one, in the green pathways, and it's very hard to scatter to the red pathways because it's very far away separated. So okay, in summary, for here we can see that in these systems now the transport is a very low dissipation and the back scattering are suppressed in these systems. Okay. So let's see what will happen. So let's see what we have got now. So we first have a carbon nanotubes. Carbon nanotube is a conductor. The armchair carbon nanotube is a conductor. We will have states and it can conducting electrons and everything is good, but it's a trivial conductor. If there's impurities here, it's very easy to be back scattered from here to another because this back scattering is very easy to happen, because there's no topologically protected. And for boron-nitride nanotubes, it's an insulator. So there's no states here. So it cannot conduct electrons. So it's an insulator. But if we combine these two together, we can get a topological conductor. Now it can conduct the electrons just like the pure carbon nanotubes. And also more, it's topological protected. That means that the dissipation here is very low. There's no back scattering here, just as I said in this picture. So in summary, we just combine a trivial conductor, which can conduct electrons, but the efficiency is very low. And we have an insulator. It can't even conduct electrons. We combine these two together, and we can get a higher efficiency topological conductor. This is very surprising at first sight because, as we say, just from our imagination, we have a bad conductor, we have an insulator. We combine together, we can get something between them. Maybe it's an insulator, or maybe it's a bad conductor. But the interesting thing here is that we combine a bad conductor with an insulator, we get a very good conductor, a topological conductor here. So this is the main result of my studies. So let's give a very intuitive metaphor here. So for a trivial conductor such as this carbon nanotube here, so when the electron goes inside this trivial conductor, it's just like a busy road. This road is okay. You can just drive your cars or drive your motorbike along this road. But this road has no rule. You can see that there's a lot of traffic jam here. So when you go in this way, sometimes you meet another car, or you meet some another people. This is just like when electron goes in this conductor, it meets some impurities or vacancies or some disorders. It will be bank scattered. So it's also like this. If you drive your car here, and because this traffic is very bad, so sometimes there's people standing here. So you have to change another way, or you have to just drive back. So this is a very bad traffic here. So just for a boron-nitride nanotube with an insulator. So you can see this road is broken. It's a stop sign here. So this electron cannot even pass. We just combine these two together, we can get a topological conductor, which is just like a highway. So we know that in the highway, the traffic is a very high efficiency. This is because in the highway, the cars in one direction and the cars in another direction are separated and at two sides, on the two sides. So you can see that when you drive a car here, you cannot go to another way. So this, if you have this driving experience, you know this. So in the highway, it's a very high efficiency transport. This is because that the two directions are well separated. So this is just like our topological conductor here. So with this K and K prime, so if we want to go from here to another side, we need to go from this side to another transport pathway. It's like this highway. So in this study, we just combine a bad traffic with a stop sign, and we get a highway. So this is a very intuitive picture about what I have done here. So in this one, we will know this is a very high efficiency transport in these structures. So okay, let's see what it can be applied in our knife. So we know that in our knife, this integrated circuit is a very basic part of our computers or our informatic technologies. So this is integrated circuits. So we know that in the integrated circuits, we have a lot of these conducting wires or the interconnects everywhere. So the power dissipation is a very it's the most important challenge in the integrated circuits. So this is also the most challenge for how we can increase our efficiency of our computer. So if we can replace this interconnects with our topological nanotubes here, so we can just get a very low power integrated circuits here. So this is the application of my studies here. So we can just use a concept called topological integrated circuits. We can just replace all these interconnect these wires with these topological pathways. Then we can get a very high efficiency transport and get a very low power dissipation device. So this is the application of my studies, that we can get a low power dissipation 1D material, so 1D transport, 1D conductor. Okay, so let's move on to say what's the physics inside this structure. So let's see what we have got in my studies. That firstly, we just combine this carbon nanotubes with this boron-nitride nanotubes. So if this boron-nitride nanotubes and the carbon nanotubes has the same carrier vector, it's an insulator. But if we have some difference between these two, it still has a band gap, but now it's a topological conductor here. It has a topological conducting states inside this bulk band gaps. So why we change from this M change from 0 to 1, we will get so much difference. So this is the topological. So we need to explore the topological origin inside this structure. So until now, I have said a lot of topological properties, topological pathways, topological states, and I think most of our audience are not so familiar with this field, with topological physics. So maybe you have heard of this concept in a lot of seminars, in conferences, in meetings, or in lectures, but until now, I think this is still a mystery to most of us. So in the following, I will say what is topological physics, I will help you to build a very basic background about the topological science and how it can be used and why it's so popular nowadays. So don't be afraid. I will not say a lot of mathematics or formula, this kind of thing. I will focus on the basic physical picture and to let you know some basic background about this this topic. Okay, so first thing, what's topological physics? What's topology? The concept of the topology is from the mathematics. A branch of mathematics is called the differential geometry. So the topology concept is from this branch. Is that we just ignore all these formulas. Let's see what we can study here. So we know that there's a lot of these shapes. We have a lot of objects in our life. Many years ago, I think it's several hundred years ago, and we can see that some mathematics scholars found that if no matter how strange your surface is, for every point of this surface, we can define a curvature. This is just like we know this, so we can have a lot of curvatures here. For each point, we have a curvature. So we just integrate this curvature, this curvature around all the surface. And a very strange thing happens is that no matter how strange our surface is, this integral is you can see it's an integer. So this formula here, we just integrate this curvature and we just divide it by 2 pi and use this formula. We can get the integer here, and this integer is in fact is how many holes of your objects, such as for sphere, for ball, or for orange, for apple, all these kind of things. We have no holes. So this number, we just calculate this number. We can get this number is 0. So this number we call it topological number, or we call the topological invariant. It's because it cannot change. It's invariant. So it's a topological number here. So no matter you give me an apple or orange or this kind of thing, there's no holes. So the number is a constant. It's a 0 here. So for some other objects, such as the donuts here, or a cup here, so we'll see that there are 1 hole here. So if there's 1 hole here, this number, topological number is 1 here. So if this we can see this donuts and this cup has a totally different shape. But if they have the same topological number, they can reshape from one to another without breaking any holes. You can see that I think I can give a GIF here. You can see this video. When I see this from one, you can see that this they are equivalent. So even though they look quite different, but they have the same number of the holes, so they can reshape from one to another. So we can say that if these different objects, these different shapes, belong to the same topological class, they have the same topological numbers. So, or we can say they have the different numbers of holes, so they can continuous deformation from one to another. So this is the basic concept of the topology in mathematics. So this is nothing about the physics, but some physicists just extend this concept to material science, to the condensed matter physics. Is that we know that here we will just define this curvature not in the real space, we just in the K space. I think the material researchers should know this very well. So we just do Fourier, because for the real space, such for a crystal, it has a transitional space symmetry. So we just if we have the transitional symmetry, we can just do the Fourier transform from this real space to the K space, or we can see the reciprocal space. So this is they can just be transformed from this Fourier transform here. So we can just define our properties in the K space or in the reciprocal space. So in the reciprocal space, we can just define a Berry curvature, called Berry curvature. Firstly, we just skip this formulas here. We can just see that we can for crystal or for material, we have the Berry curvature. We can see this Berry curvature is very similar as this this curvature of this objects. And also we can just integrate this barrier curvature around all this K-space, just like we just integrate this curvature around all this surface. And we can just get some numbers, just like you can get numbers, the holes here. But now it's not holes, it's some physical quantity here. So we call this holes, we call this numbers here. It's a Chen number. I think some of you may hear this before from some seminars. So this we call it Chen environment or Chen number here. So this is in memory of our, I think it's a Chinese American scientist, Chen here. So this is he's a mathematical scholars, but because all this are from mathematics, so we just use this number with his name, the Chen number. So it's just like how many holes. So we just skip all these formulas here. We just think about that. This is in fact how many holes, just like this in this shapes or these objects. So we can also use this Chen number here to classify different materials, just like we can use this how many holes to classify different objects. So for this one, we call the topological class. So if we have different materials, such as if we have this materials, if we have two materials, such as we have two insulators, insulator A and insulator B, and we have different numbers of this, we have a different number of this topological number here, such as one is CA and one is CB. So an interesting thing is that this is just like we have left we have a downloads and the right one we have a ball, so they are different. So the interesting thing is that even though this one is insulator and this one is also insulator, but at the boundary or at the edge, they are conducting states. This is something like, so we can just think that if this structure from this one to reshape to another one, we must break these holes and then reshape. So this when we break these holes, we just create a states here. So this is a conducting states. So let's see what will happen in the band structure. We can say that if we have you can say that there's a band gap because this is an insulator here. Both of them are insulators, but because there are some we can see the phase transition because this one and this one belong to different topological class. So around them there are conducting states here. So there's an edge state here, or boundary states here. So this is the most important consequence of the topological physics is that the bulk is insulating, but the boundary is conducting. So we can say that in this band structure, we can say there's a conducting state here. Then the conducting states we call the edge states or boundary states, and these states are from this edge atoms here. So and this edge you can see there's no bank scattering, as I said before, because there's no states forward. There's no states bank forward. So we can say that the electron can only go from this to this edge to this edge and cannot be bank scattered because there's no states here. So in this system there's no dissipation. So in this topological phase transition, we can say this is just like a phase transition because the left one has a phase 1 topological class, and this one is phase 2 topological class. And inside this boundary, there are some conducting states, and the conducting states is no dissipation conducting states. So this is the most important consequence of the topological science, and it tells us that when the topological number changes, these edge states will happen. Okay, let's go back to our systems. So why we have this topological states? Just as I said, the topological states are from the topological phase transition. We need two sides and two paths, and one is from one topological class, and another one is from another topological class. And then inside these two, we can get these topological states. So let's see why we can get this topological physics, topological channels inside these heterostructures. So to analyze this, we just unfold it. We just extend this 1D materials to the 2D. We just unroll it up from this one. We just unroll it to the 2D lattice. So we can see that for this kind of structure, this heterostructure, we can get a Murray pattern here. What is Maury pattern? Maury pattern is something like you just have a very large superlattice, and at different places we can have different atomic structures. So I just give some example case here. In fact, there are these different structures change from one to another. It's very slowly or gradually or smoothly. And then we just calculate this topological number. We just call the Chen number here. So just like I said here. So firstly, we need to calculate the Chen number and to see what's happened if there is a difference between the Chen number here. So I just calculate the Chen number here. So just as I said, I will skip all these formulas. I just use some formulas here, and then this is the result. And from here, we can see that for some configurations or for some structures, this Chen number, this topological number is a -1/2, but for some of them are +1/2. So when it's rolled up to a tube, we can see that this is a cross-section view. Just cut it. This is a cross-section view, circumference. So we can see that along this one, for some of this, we can see this light blue one. For this light blue one, the topological number is 1/2, and for this purple one, it's -1/2. So just as I said here, when one side is one topological number and another side is another one, along this boundary there should be the topological states. So this is the topological origin of why we can get these topological states in our system. Is that we have some topological, you can see this number changing here from positive 1/2 to -1/2 here and also here. So we can also compare, or we can also compare this with this the topological states. So this red one and this blue one are the topological states, the atoms contributing to the topological states. So we can see that they match very well. So this is the origin why we can get topological states here. That is because along this circumference, there are topological phase transitions. So this is all the physical origin here. Is that we just combine this carbon nanotubes and the boron-nitride nanotubes. There's a Maury pattern here, and the Maury pattern have different configurations, and different configurations give you different topological numbers. And when the topological number change, we can get the topological states, which is conducting and which is no dissipation. So this is the whole story. So finally, let's see something more interesting here. Is that in fact we can roll it up, just like I said. All these carbon nanotubes are rolled up from this 2D lattice. So we can also roll it up from another direction. So we can see that if we roll it up along this spiral way, so now we can expect that this conducting states. You can see that the conducting states now is spirally wrap these nanotubes. So you can see that. So now it's not a straightforward. Now you can see it's a spirally wrapping these tubes. So if we just connect it to a circuit, so the electrons or the carriers will go like this spirally. So it's just like a solenoid. So I think all of us have studied this solenoid in our high school or in our undergraduate studies. So we know this solenoid in our traditional solenoid. These are coils. These are some copper or some conducting materials. They are coils. But for here, this conducting pathways are topological conducting pathways, and it's a very, very small solenoid. So I can just give a comparison here. So we know that this Ampere's law is that the electric field of the solenoid is proportional to the coil density. The coil density means that how dense coils has been wrapped in this tube here. So for our macro scale solenoid, which we can buy in the shops or through the online Amazon, we can buy this kind of micro scale solenoid. And for this kind of thing, we can see that this N. So for 1 meter length, for 1 meter length, we can at most have 1,000 of this tens of these coils. But for our nanoscale topological solenoid, because this you can see that the distance between two coils are very close, and it's a nanoscale. So we can get a very dense this coil density here. So I can get we can just give an estimation here. One is mu amperes current can generate this magnetic field. It's 1.6 Gauss, and it's 5 times larger than the magnetic field of the Earth. So this is a very remarkable magnetic field here. And also, just as I said before, this current, inside this current flowing in the tubes, and it's no dissipation. So it's no power dissipation transport. And also it can generate a very large magnetic field because this coil density are very dense. It's much denser than the micro scale solenoid here. Okay. Finally, I give an overview or a summary of my studies that I just combine the carbon nanotubes with boron-nitride nanotubes. A carbon nanotube is a conducting, is a conductor, but it's a trivial conductor. The efficiency is very low. And the boron-nitride nanotube is the insulator. I just combine a very low efficiency conductor with the insulator, and then I get a topological conductor, which has a very high transport efficiency, and it has no dissipation, power dissipation, and it can help us to save energy, and it can help us to promote our computer abilities. So, and also we can just get this topological, these pathways in another ways, and we'll get this topological solenoid, which can generate a very large magnetic field. So this is the whole picture of my study. Okay, thank you for your attention, and also thank you for all of you come here. Okay, I'm done here. You are mute, Dr. Ying.
Can you hear me?
Yes, of course.
Yeah. So yeah, I have very interesting talk, and I actually thanks so much for the talk, and I actually have a lot of questions for you actually.
Okay.
Yeah. Let me I'm not sure if anyone else has questions, but I do have some. The first thing is that we know that the carbon nanotubes and boron-nitride tubes, in terms of the structure, they are identical to each other, but one is a conductor and the other one is insulator.
Yes.
I mean, what actually caused the difference? Like, why is because in terms of structure is exactly the same. So what caused the difference that one is insulator and the other one is the conductor?
Okay, I can give a very a simple picture here. So this is because the chemical bond strength. So for the let's see here. So you can see that in the carbon nanotubes, all they are carbon atoms, right? So
yeah.
So for the carbon atoms, so the hybridization is sp2 hybridization. So they are very. This is a very weak bond here. So we can see that all these chemical bonds are very weak. So it's a pi bond. We call it a pi bond because it's a very weak chemical bond. But for this boron-nitride, this chemical bond is very strong. So if this chemical bond is strong, you can see that the atoms are very low. You can see the electrons are very localized as just around these atoms. It cannot move freely from one to another atoms. You can just
I see.
Because they are very strongly trapped around these atoms.
Okay. So actually another question is kind of related to because what you do for the topological conductor is that you actually put the carbon nanotubes inside the carbon nanotubes outside the boron-nitride tubes. I mean, because I know they have a very famous work Yuan's house work. They actually using a magical angle, using two graphene layers. And I'm just wondering, what if you actually put instead of using boron-nitride nanotubes, you're using another carbon nanotubes. But the the orientation of the two carbon nanotubes is a bit different, just like as you show in the previous slides. What happens, like for example, you are having the exactly same or similar metric angles between those two carbon nanotubes. What happens? What might happen?
Okay, this is a very good question. Is that we can say that all our work is based on the Murray pattern here. So the Murray pattern is now, I think, is the most important topic in the 2D materials or the 1D materials. So we can say this is the Murray patterns here. So the Murray pattern has two origins. The first one is that if we have two lattices, and the two lattices has some mismatch. So so they can naturally form this Murray pattern because one is larger than another one, so they can get a Murray pattern. Another one is like I think it's what you said is Chaoyuan made. It's that we just have twins. We have the same material that we just twins with each other. So it has orange. So we can also get this kind of Murray patterns here. So in my study, what I used is the first one. Is that because the boron-nitride nanotube and the carbon nanotube, they are naturally different. They have different this constant, this lattice constant. So if we combine them together, they can naturally form this Murray pattern. But if we use a different one, such as both of these two tubes, we use the same carbon nanotubes. Yeah. And we can also twin them together. We can also get this Murray pattern. We can expect more interesting properties. I think our topological physics can also happen in this kind of structures. These Murray patterns can induce a lot of interesting properties, such as the superconducting, topological conducting, and all this kind of, such as this some strong correlation, conducting, all this kind of things. So this is a very hot topic now. I think in my system, if I just use the Chaoyuan strategy, where I just twins the two tubes together, and I think we can also get some interesting properties.
Okay, cool. Yeah. So actually, another question I would have is because I'm not from the field, and yeah, just this slides, and it's because like because just that you said on topology, like because one topology is when G equals to 0, then you have like insulator, and when G equals to 1, you have another insulator. It means that the transition in between must be a conducting phase.
Yes, exactly.
So my understanding is that that conducting phase, like if it's on the tube, then the conducting phase will be like a line, but the one you shows here is like a phase. So
okay, so you mean that why there are some? So can you see my mouse here? I'm not sure.
Oh yeah, I can see it.
Okay, so you mean that why there's no? It's not a point. It's a
yeah. Well, why it's not a point? It's like you know an area of that.
Okay. This is also a good question. So first, I have 2 points to state here. The first one is that in fact, even though in this kind of states, it's not just one line. In fact, this also have a region, but this origin is very small. Sometimes this is so it's not a pure 1D line. In fact, it has some width here.
Okay.
So this is just for a demo here, and also for in our systems, because you can see that this you can see that the structure here is a very continuous or smoothly changing from one to another. It's not a sharp edge here. So if we have a insulator A here, insulator B here, and this is a sharp edge, so we can get a very sharp this state here. Yeah. And this width will be very small. But for here, we can see that all these configurations change from one to another. It's a very smoothly change. We can see that there's no sharp edge here. Yeah. So for this kind of thing, this area will also be, the width will be also a little larger than this sharp edge here. So it's a continuous edge. You can see the smooth edge. It's not a sharp edge.
Okay, I see. Oh, okay, I see. Because it's like more like a continuous change.
Yes.
So that's why the transition is not a line. It's not like
yes.
band.
In this system, we don't have an edge here. You see, this is a periodic structure. This is periodic. It's infinite. So we have no edge. But for here, we have boundary. A very clear boundary here. For here, we have a lot of structures just from change from one to another. It's a smoothly change.
Okay.
You know what I mean? So it has no edge. So we can just get a region here, an area here.
Yeah, I see. And yeah, also like, because like I was confused on what K means, if you remember, like last time I talked to you. But now I think I can't. But after this talk, I think I can kind of get like what K means. Like, but I just want to explain it in my way. So just correct me if I'm wrong. So what K means is actually, for example, you have a lot of atoms in a structure, and so one way to actually quantify the location of those atoms in 3D space, yes, by the coordinates, like in real space.
Yes.
And but the other way is like now I kind of like, I feel like I might be understanding that is that now, because it's not that easy to actually to model this kind of things in like a real space. So what we can do is like, because I feel like this kind of atomic structure, they are kind of like have certain frequency of periodicity.
Yes. Exactly.
So meaning that I can actually turning the real space coordinates into like some kind of like a frequency. Like doing a Fourier transfer and turn into a frequency space, like what do you call it, K space. So those K actually meaning two things. I feel like the one thing is like for it's more like it's like orientation of something like an orientation of the structure. But it actually like so if you can go to the next slide, slide 14, the next one. So it's something like means that, because now I understand why K has an arrow, because when electron like moving within a structure, it has to has a moving like along the structure, then that K actually is a vector, because the movement of the electron has a direction.
Yes.
So that's why in the transition line between the two insulators, the pathway can only be unidirectional, like one direction, because because based on the right figure, it means that the electron is moving from the for example, from minus pi divided by a to pi divided by a. Then that line, I mean, that tangential line is only one direction. That meaning that there is only one direction. There's no backside the scattering.
Yes. In this band structure, in fact, in the solid state physics. So we can know that in the band structure, the slope of this line means that the velocity. So when the slope is you can say if the slope is larger, it means that the velocity is larger. So the electron can go faster. You can just think like this. So if this slope is a positive slope, that means that this electron has a positive velocity. So we can say that the conducting states here. There's no states in the negative slope, right? There's no states like here, like this. So there's no states in the negative directions moving so in the states we can say like here. It can only goes from this side to this side. You can, if there's a states like here, like this, then we'll have a states here, like this direction. So because in this structures, the boundary states has only one. You can say it's not one pair, it's only one. So there has only one directions. So there's no bank scattering, because there's no states backwards.
Yeah. Now I think I kind of understand, because not from this field, but I just trying to understand in my way, like.
Yes, yes. I think you understand is the picture is okay. It's fine.
Okay, yeah. So because like the basically topological like conductor is that because there's no bank scattering, so I think there's one picture that you show it with some highway pictures like
Yes. Yeah.
yeah. So yeah, that's very intuitive. I mean like so I understand that because you can't like making this kind of pathway into one way so that there will be no less resistance, less dissipation. That I understand. But the way you act, but the thing is, the way you do it is like, although like you have no resistance, but you have a narrower path.
Yes.
So well, it causes some drawbacks, like comparing to like, for example, even though the other way, like they have a lot of resistance, like for example, there's no like one-way direction, one-way like
Yes.
pathway, but the pathway itself is larger and wider. So is that will be causing the you know what I mean, like
Yes, yes, yes. I totally understand what you are saying here. So for here, in fact, what you have said is very correct, because for the total current or for the total transport, we have two factors. The first one is how many channels, right? How many pathways. The second one is that how efficiency for each transport. So for this one, so in this one, I have solved one problem, is that for this topological conducting, the efficiency is very, very high. It's much higher than the trivial one. And also, in fact, we can also just make more topological pathways here. I didn't show it. I didn't show up here because I think I just deleted this page. So I can tell you that we just go to this this page. What I want to say is that, in fact, I can not only get two, I can get what I want. We can get a lot of these topological pathways, not just two. We can stay here. So if we have one this topological phase transition, we can get one pair, right? Topological channels. In fact, we can get a lot of this transition points.
Okay.
So they can get a lot. So how we can get a lot of these topological transitions? In fact, we can just choose one parameter. It's M here. You can see. So if the M is 0, that means that there's no Mori pattern here. So there's no topological pathways. If the M is 1, we have one pair. If the M is 2, we have two pairs.
Okay.
Because if the M is 2, that means that we have two periods of this Mori patterns. We can just when I think of this one, we just have another period. So now we have two pairs of this topological phase transition. So we can get two pairs of the topological pathways. So in fact, we can tune this number of these topological pathways. So no worry about this. There's a number of the topological pathways. We can tune it.
Okay. Yeah. I think I can.
And the way to tune this or to modulate this number is very easy. Is that we just change the number of M. The M equals how many pairs of the topological pathways. If M is 0, there's no. So that's what we get here. There's no, because the M is 0. I mean, if M is 1, we get one pair. I didn't show if M is 2 or 3 what will happen. In fact, if this the number of M equals how many how many pairs of these topological pathways.
Okay.
This is a good question, but we have solved it.
Okay, yeah. So, but another thing is that I know that within the, for example, if you like put two have nanotubes together, stacking it, and I know that there are chemical bonds between like within each layer, within each tube. But what's the bonding between two tubes?
Okay.
Like if there's no bonding between the two tubes, then it means that one tube can have relative motion. Then the topology of not topology, the topology like of the structure might change, right? So you can move freely.
Yeah, I get a meaning. So between these two layers, there are no chemical bond. So this is not so the orientation is not fixed. Between the two layers, there's a force. I don't know if everybody is familiar with it. You will call the van der Waals interaction. So it's something like a very weak Coulomb interaction. So it's not a strong chemical bond. So between these two layers, just as you said, it can slide with each other, and it can also just rotate with each other. This is what you want to say, right?
But what I understand is, in order to have this kind of topological conducting and the phenomena, you need to have you need to actually fix the relative position between the tubes.
Good question. In fact, this is also a question this is also a question that my PhD committee member asked me.
Oh yeah.
So this is a good question. So that for that question, in fact, what I want to say is that these two layers can relatively move or relatively rotate or relatively slide with each other, but it doesn't matter, because no matter how you change, this Mori pattern exists here. You can see the Mori pattern here. The Mori pattern exists, and if you just rotate move with each other, some relatively, maybe the Mori pattern will change a little. So maybe this boundary is not here. Maybe it changes to here. But it doesn't matter, because this will always happen, because this topological phase transition happens.
Okay.
So maybe
I think because the structure is periodic, so no matter how it moves, like it was always like center.
Maybe you will change the different places. Maybe this you can say maybe this topological pathways is not here and here. Maybe it's here and the inside way, but anyway it will happen here.
Okay. Yeah, I think I kind of understand, because so it only changes like the location of where the pathway is.
Yes.
Yeah, I see. Yeah, so let me check if I actually have some other questions. Another one is like because like both from your work and Yuan Cao's work, like I know that you have two layers of some nanotubes, like carbon nanotubes or boron-nitride nanotubes, or graphene layers. What happens if you like having like a multi-layer stacking? Like
you mean maybe above two, maybe three?
Yeah, above two. Like, but it's like in the stacking direction, it is also periodic. Like you just keep on stacking these two layers, or you have I mean, or you can have some other like stacking, like
yes, of course, yeah.
So for example, let's just have like a periodic two-layer stacking, meaning like you just keep on stacking these two layers, like will the phenomena become different, or you just like or just have the same phenomena, or what?
For my structure, I think the phenomena will not change a lot, but for such as for Cao Yuan's work, I think maybe it will change, because in my work, in fact, between these two layers, just as I said, this boron-nitride and the carbon nanotube, these two layers are very weak van der Waals interaction. It's not a chemical bond. So when you stack one AB one with another, in fact, it will not change a lot with the property, because all the properties are from this carbon layers. That the boron-nitride, these layers, they are just providing some very weak interaction. So I don't think it will change a lot. But for Cao Yuan's work, I think it will change, because Cao Yuan's work, these two carbon nanotubes have a very strong chemical bond. So if it has a chemical bond, if one A is here and B is here, and if another A is here, in fact the B will have two interactions. One is from the upper A, and one is from the lower A layers. So the chemical bond will totally change. In fact, this what you said, this multi-layer heterostructures or multi-layer Mori pattern now have attracted a lot of attentions. I think a lot of literature about this. They indeed got some different properties, which I think is new and fresh, which didn't show up in the bilayers.
Okay. Yeah. Yeah. And another thing, like, oh yeah, another thing is like, because I'm not from the nanomaterials background, but in general, like when you like manufacture those kind of materials, usually you will always introduce defects within the materials.
Yes.
So there will be topological defects within the materials, and with that defects and the impurities like affect the performance or the phenomenon what you have here, like in real world. I mean, so what I feel like, because it's highly depending on the topology of the local structure. So if you have an impurity or defects, then it will disrupt the topology of the structure. So
Okay. So this is a good question. In fact, it's very hard for me to answer this question because I'm not an experimentalist. So I don't know how. So, but according to what I have learned from the literatures, the experimental literatures, so in fact, such as if you want to break this kind of topological physics, you need to such as give some vacancies or disorders, or some, we can say just some atoms are missing, or just we replace another atoms or something like this. So I think it will affect the topological physics here. Such as if we just remove one atom, I think this topological physics will, the topological number will change or something. But according to the literature about this carbon nanotubes, this kind of defects are always happen at the end of the nanotubes. It will not happen in the bulk of the nanotubes.
Okay.
So it will not affect or not, because for this carbon nanotubes, it's a very strong chemical bond along this atoms and along these tubes. So I think most of these defects or disorders will happen at the end. So I don't think it will affect or not to my results. Okay. I don't have the results. I don't have the result in the carbon nanotubes, because this is a new study, and it is also a new prediction to the experiment. But I have some literature. It's about the graphene. The 2D materials graphene. For the graphene, the defects will not affect or not to the topological class, to the topological physics. So I think the nanotubes will also endure this kind of defects, but I'm not sure, because this is a new theoretical study. I don't know if the experimentists what will happen to them.
Okay.
But from the experience from literature of the graphene, I think it's okay. It's good.
Okay. Yeah. So I guess yes, because it's local, with its local defects, and I guess like it's all right. I'm not sure because I'm not from the field, but so in general, like because all the detailed question, like I pretty much done with that, and we're just like interested, like what are you most interested in, like future directions, or maybe move towards like an experimental, and what's your like what's your plan for the future research on this kind of topic? I mean, it doesn't have to be too much details. It's just like roughly what kind of topics you are most interested in.
Okay, so firstly, in the following, I will also still focus on this Murray patterns, because Murray pattern now is a hot topic in the no-dimensional systems. So for the 2D Murray patterns, I think one direction is that what you have said is that I can stack more layers, not just 2 layers. I can just stack 3 layers, 4 layers, and multi-layers. And we can get more complicated and more interesting Murray patterns to see what will happen and what we will get different from the by layers. So, and also another direction, interesting direction, is the hetero nanotubes. This is the 1D Murray pattern. And of this one, you can see this literature. You can see this is 7 years ago, but this is this year. So you can see this field is much more new, I think, in this field. So this is also a new field. It's a 1D Murray pattern. So this is what I want to do in the next. Is that we just study another system such as MOS2 or another kind of systems or black phosphorus systems, other materials.
Yeah. And also like because I know have nanotubes, and all those nanotubes are very, very small. So what kind of technique are you using actually to put these two nanotubes like stacking together? I mean, what I feel like it is very precise. Like, so I don't know how you can do that. Yes, like I mean, stacking layers I understand, but stacking two tubes, it's like super high precision.
Okay, so this is a good question. In fact, you know, for our for us theoretical this kind of studies. So when we submit our manuscript to some journals, the most challenge question is that, do you have experiment? How you can prove your design is realistic? It's not just by your imagination. So this is always a tough question because we are not experimentalists, so it's very hard to answer. But the very interesting is that in this study, in fact, this kind of materials has been done in the experiment many years ago. Or not many years, I think it's 6 years ago. So this kind of experiment has been done. But the question, so the interesting is that when I think it's ACS Nano is published. I think it's in 2016 or 2015.
Yeah.
There's a paper. Is that there's an experimental paper? Is that they just fabricate this boron-nitride nanotubes and the inner is the carbon nanotubes. But the interesting thing is that at that time they didn't realize that it's a topological system. Their motivation is that because they know that the carbon nanotube is very interesting and it's very useful, but the carbon nanotube is very sensitive to the environment.
Yeah.
When you fabricate it in a solution or in some other environment, it's very easily it is very easily broken by the environment. So the boron-nitride nanotubes are very stable. So their original motivation is that they use the boron-nitride nanotubes to protect the inner carbon nanotubes.
Okay.
So, but they didn't realize that in fact this is a topological systems. So when I saw this read this literature, I found this is very interesting because always our experimentalist goes far away than our theoretical physicists because they have done, but they didn't realize it. By the way, after this prediction, we can know this can be done. And you can see there is also literature here. This is a science literature. This you can see this is just published this year, and they also fabricate this kind of hetero nanotubes.
Okay.
In the experiment. And
I can see they have like a multi 3 layers. Like
yes. And this paper is published after our paper, so they cited our paper. They said that by this way they can get the topological physics, but unfortunately they didn't get it. And they also give some comments, and they also give some reason, some explanations. They said that okay, our fabrication has some shortcomings. So they didn't realize this topological physics, but they said that they can do this because they said our paper. They said that this is a very good direction, and by using this heterostructure, we can get topological physics. But we didn't get it. But I think in the future we can get it. This is what they said in their science paper.
Yeah.
So they have done this kind of thing.
So that's interesting. But like because speaking of the fabrication, or just like suddenly there's some idea comes in. Like so I know that the way you actually do carbon nanotube is like you roll like a sheet like a graphene layer into a carbon nanotube. Is that how it was done?
No. This is the roll it up. This process is just a demo. It's just
I see.
It's just from our imagination.
Okay. So my question is, what if you actually roll it like rolling a paper? So
you didn't roll out. The carbon nanotube is not by roll it up. It's not just.
Yeah, I know. Like I'm not saying like to fabricate in carbon nanotube. What I'm saying like you just roll a graphene layer, a graphene sheet.
Yes.
So it's just like rolling a paper. So it will not be like a closed loop geometry. It will be like open loop geometry, but it is just like in a row. So is that possible to introduce some, because it's kind of similar to like tube within a tube, but it is made by one row. You understand what I mean?
You get the meaning. So in fact, both this carbon nanotubes or boron nanotubes or even this hetero nanotubes is not by rolled up. So it's not just we have 2 layers and we rolled up. I don't know if it's possible for the experimentalist to do this rolling up.
Yeah, what I'm saying is not to fabricate. It's not to roll. It's not to roll a graphene sheet into a nanotube. It's like just rolling it.
Yes, I think it can be done. Yes, you are saying that if we can just roll it up to maybe to another shape or
yeah, just roll it up like
yes, it's possible.
It's like rolling a paper, just like rolling a paper. You can roll a paper into a tube, but it is not a carbon nanotube. It's kind of like a tube made by graphene.
The graphene can be rolled up, but I didn't see any literature that it can be rolled up to a nanotube, but it can be rolled up to another direction, such as, so if you have a layer, they can do like this. You see? This
okay.
Kind of thing. This is possible, but
so what I have in mind is like to keep rolling until it was like some kind of like tube like that.
I think this is what you should answer. You are an experimentalist. I'm not experimentalist. I don't know.
No, I'm not.
In the theory, I think it's possible.
Yeah, I'm not in the nano world, so I'm not so sure. Like, I'm not 100% in doing experiments, so yeah, I don't know actually. I mean, just like it had just occurred to my mind, so I was yeah.
In theory, I think it's possible.
Okay.
But you know, from what I've read in the literature, so I didn't see any of this.
Okay. Yeah. Okay. Yeah. I think that basically conclude all my questions. Like because it's very interesting to me. It's new and it's very interesting. I actually learn a lot from today's talk. Yeah. Yeah. So you can see like I actually make a lot of progress like last time we talked.
Yes. You have learned a lot.
Yeah, I truly learned a lot. Yeah. So I'm not sure if any other people would have like questions. Does anyone have? If there's no questions, then I will just maybe conclude our today's seminar.
Okay. Thank you.
Yeah.
Thank you
I mean, thanks so much again, like for all the hard work on this talk. Yeah, I really appreciate it, and yeah. So yeah, please also give me some feedbacks on the on how we can making like changes in this kind of talk series, and how I can make improvement on that. Yeah,
okay.
Yeah, and thanks again for Dr. Hu. Yeah, applause.
Thank for all of you to come here.
Yeah.
Thank you.
Yeah, thank you. Bye.
Bye. Good night.
Bye. Good night to you.